A common way to determine muzzle velocities for guns and other objects, or any object that is moving incredibly fast, a common way to determine its velocity is using something called the ballistic pendulum, as shown here. The way it works is you fire the object into a large pendulum, or at least a pendulum that has a much higher mass. The object will get embedded inside of the pendulum. This would be an inelastic collision, and then as the result of that, you'll have a final velocity from that inelastic collision that then will cause the pendulum to swing upwards some height. And that final height is easy to measure here. Then, from that final height, you're able to calculate backwards through this process, backwards from that height to this velocity, and from that velocity over to this initial velocity of the projectile, how fast the projectile was going. So let's go ahead and let's do that. We have a bullet that is going some velocity, v naught, and that's what we're going to solve for here, v naught. It has a mass 7.3 grams, and it's going to hit and lodge itself in a pendulum that has a mass of 1.2 kilograms, causes it to rise 19 centimeters. How fast was it going? First step is to go ahead and calculate the initial velocity that this pendulum began to swing up with. So I'm working backwards here from the height to how fast it was going before it started to swing up to, and that's the final velocity in the collision, to the initial velocity there before the collision. So this is a conservation of energy problem here. I have some initial velocity, and it causes the pendulum to reach a maximum height of 19 centimeters. At max height, final velocity is 0. So all I have is initial kinetic energy, and that's going to be translated all into potential energy. Now I'm going to work this problem through all the letters and substitute numbers in at the very end. As you can see here, though, the masses are going to cancel out because I have m plus little m, capital M plus little m, standing for the mass of the pendulum plus the mass of the bullet because they lodge together. I have them on both sides, so they cancel out. All right, so now I've calculated all the way back to how fast the pendulum was going right before it began to swing up. In other words, how fast it was going immediately after the collision. Well, the initial velocity of whenever it's swinging up is the final velocity after the collision. So I can use that in a conservation of momentum problem. This is an inelastic collision. So I write the inelastic collision equation down. I have the bullet and then the pendulum separate in the beginning initially, and then finally they're going to combine. And the initial velocity of the upswing is the final velocity after the collision. I mean, think this through. You have your initial velocity, you intersect, right? It collides, causing a final velocity, which then causes it to swing up. So I'm working backwards now. I already know the momentum of the pendulum before the collision. It's going to be 0 because the initial velocity of the pendulum is going to be 0. By the way, I'm using VI in a lot of these. You could use V naught for initial velocity and just V's instead of VF's for final velocity. That would be fine as well. Now we need to substitute in what the final velocity actually is, and that will let us solve around for the initial velocity of the bullet. And solving this all around, I come out with square root of 2gh times m plus m, all in parentheses, the pendulum mass plus the bullet mass, all divided by the bullet mass. And there's not much simplification that could come here. I mean, I could distribute things out and make it maybe a little bit cleaner, but I don't feel the need to do that. I'm just going to go ahead now and plug in numbers and get my answer. And so after converting here, I should point that out. You want to convert your centimeters to meters, so that'd be 0.19. And you also want to convert your grams here to kilograms, 0.0073. You come out with using 2 sig figs, because that's what seems to be given in the problem, 320 meters per second. I will also mention this. A lot of times, whenever you see this happening here, the little m will be neglected. It won't even be added in, because 1.2 kilograms plus 0.0073 kilograms is practically 1.2 kilograms. It's multiple orders of magnitude off. So a lot of times people will neglect the mass of the bullet altogether. One last problem to try to get this idea of how energy and momentum can intersect here and how they both are very useful. I have 2 carts that are attached together with a spring. Maybe there are 2 hands scrunching them in, and the spring scrunches a displacement delta x inwards away from equilibrium. The equilibrium, its normal standard length. If you just let it be as it would go to its equilibrium. So we scrunch it in some displacement delta x. And then the 2 hands release it, maybe you cut a string, whatever, and so the carts shoot off. One cart shoots this way and the other cart shoots this way. This cart has a mass m, and this cart has 2 times m. Those are the same m's there, so this one is twice as heavy as this guy. And I'm looking for what is the velocity in all letters, what is the velocity of the cart with mass m on it. So you can see from this problem, it's just a simple explosion, and it is explosion, although it will require a couple other steps. This is a standard explosion problem, so you go ahead and you write your explosion equation down and substitute in what you know. And since all I know are the masses, m and 2m, I go ahead and substitute those in. I also purposefully gave a little bit extra notation, final velocity 1, final velocity 2, so I don't get things mixed up. I'm going to call this cart 1 and this cart 2, and if I just left it VF, I might get those things backwards. Well, here's an issue. I don't have enough information. I can easily see here that the m's are going to cancel out. I have an m in each one, so if you divide both sides by capital M, the m's completely go away, leaving me with negative final velocity 1 is going to equal 2 final velocity 2. This type of idea is something that you'll find common where they're talking about ratios, and so just from this idea where the masses cancel out, so this would be, by the way, a good multiple choice problem where it's asking about what ratio might the velocities of these two carts in an explosion have. You can see that the cart 1 is going to have twice the velocity of cart 2. We're going to have to multiply cart 2's velocity times 2 just to get it up to whatever cart 1's velocity is. But this still isn't my answer. I'm looking for the velocity of cart 1. I don't know the velocity of cart 2 yet. If I knew it, then I could solve. I have two unknown variables. Whenever you have two unknown variables, you must have two equations, and I have only written one. Let's write a second equation, specifically from the conservation of energy. Where's all the energy that these carts where's all the energy that the carts get? Where does it come from? Well, it comes from the spring, and so let's maybe just start out. We'll write spring energy. So potential energy in a spring, and then it's going to go into the kinetic energy of the two carts, kinetic energy of cart 1 and kinetic energy of cart 2, KE2. So now I can just substitute in what all those equations are. Potential energy of a spring is 1/2 kx squared delta x squared. And then kinetic energy is 1/2 mass times velocity squared, and I put in those masses for those two carts, keeping them with the correct velocity. Now you can also see that this 1/2 and 2 is going to go away there. 1/2 times 2 is 1, so that completely cancels. Now let's examine what variables there are in this equation. 1/2, obviously a number, k, now that's a constant that would be given to us. We're allowed to have our answer in terms of k. Delta x would be given to us as well. 1/2 m is a constant that we're allowed to have in our answer. Final velocity 1 is what we're looking for. M, another constant that would be given to us, allowed in the answer. Final velocity 2, not given to us, not what we're looking for. That would be a variable. I have two variables, VF1, VF2, in this equation, and two variables, the same two, in that other equation. So I can use substitution to solve this. Since I'm looking for the final velocity of the first object, I'm going to solve this equation around for VF2, and then substitute it in, which will allow me to solve for VF1. So doing my squares here, squaring the half and then squaring the VF, notice these are multiplied, so that square can go to each of them individually. I come out with 1/4 VF1 squared, and now it's just simple algebra working towards VF1. I had to go back in. I forgot my squares up here from the VF1, so I had to add those back in. Now I can combine these like terms. Now 4/3 times 1/2 happening right here. I got 4/3 m 1/2 kx squared, so I can multiply my 4/3 and a half, those two numbers together, to simplify that. And then of course simplify that down to 2/3, so that becomes 2/3 mk delta x squared equals VF1 squared, and we finish it off with the square root. Trying to simplify down a little bit more, since all these are multiplied, I can actually separate them out. 2/3 square root of 2/3 mk times the square root of delta x squared, which then of course allows me to get rid of that square there. So I end up with square root of 2/3 mk times delta x equals VF1. So that gives me the final velocity of the first object. Now, of course, if I wanted the velocity of the second object, I would just simply take this right here and plug it back into the momentum part. This momentum equation up here would probably be the easiest to plug it back into. Plug it back into VF1 and solve for VF2. All right, so that gets our basic idea of energy and momentum and how they intersect, and we'll continue to expand on that in class.